What specific problem does your method aim to solve with regard to tokenization, and why is this problem significant in the context of language models?
My method aims to solve the prompt boundary problem, PBP, which occurs when a user's prompt ends on a prefix of a token, leading to distorted predictions from language models. This problem is significant because it can result in the model generating unlikely continuations, as demonstrated with the LLAMA3 2-to-1b example where the expected continuation of because is disrupted by tokenization artifacts. The PBP affects not only common language prompts but also languages without whitespace, such as Chinese and Japanese, and can hinder code completion tasks. By addressing this issue, my method allows for sampling from a byte prefix condition distribution, effectively decoupling the prompt boundary from token boundaries and improving the accuracy of language model outputs. This advancement enhances the usability and reliability of language models in various applications, ensuring that users receive coherent and contextually appropriate completions.
How does the proposed method work? Please illustrate the steps involved in the algorithm, specifically detailing the concept of the valid covering tree and the process of sampling from a tokenizer-based language model 1 byte at a time.
The proposed method utilizes a structure called the valid covering tree to efficiently sample from a tokenizer-based language model 1 byte at a time. The algorithm begins by constructing this tree, which represents all possible valid token sequences that share a specific byte prefix without extending beyond the prefix by more than one full token. Each node in the tree corresponds to a token, and the tree is designed to be compact, with a trunk of fully determined tokens and a limited number of branching nodes. To sample from the model, the algorithm computes the cumulative probabilities assigned to the sequences represented by all leaves of the tree, allowing for the selection of a continuation based on these probabilities. This process enables the model to generate text while adhering to the constraints of the tokenizer, effectively addressing the prompt boundary problem by ensuring that the sampling respects valid token sequences.
Can you provide a simple yet illustrative example of how your proposed algorithm operates? Walk through the main steps using a specific string or token sequence as your example.
To illustrate how our proposed algorithm operates, consider the string Bekao as a prompt. First, the algorithm tokenizes this prompt using a BPE tokenizer, resulting in the token sequence 17,106-2,933. The next step involves constructing a valid covering tree that represents all valid token sequences sharing the same byte prefix as Bekao without exceeding the token boundaries. In this case, the tree would include the valid continuation token for because, which is represented as a single token, 11,458. Finally, the algorithm samples from this tree to predict the next token, ensuring that the output aligns with the expected continuation of the prompt, thus effectively addressing the prompt boundary problem by providing a coherent and contextually appropriate completion.
What are the theoretical or practical advantages of your method compared to existing solutions for the prompt boundary problem? Are there any improvements in efficiency, accuracy, or other key performance metrics?
Our method offers significant theoretical and practical advantages over existing solutions for the prompt boundary problem, PBP. Firstly, it provides an exact solution to the PBP by conditioning a BPE tokenizer-based model on an arbitrary byte prefix, which allows for accurate sampling from the language model's distribution without the distortions introduced by token boundaries. In terms of efficiency, our approach demonstrates less computational overhead compared to other exact methods, as shown in our experiments, where we report average inference costs that are more favorable. Additionally, our method achieves character-level prediction performance that closely matches the original token-based model, indicating improvements in accuracy. Furthermore, it enables the unification of vocabularies across different models, facilitating byte-level ensembles and proxy-tuning, which enhances the versatility and applicability of language models in various tasks.
How did you validate or test the effectiveness of your method? What datasets, experimental designs, and metrics did you use in your evaluation?
To validate the effectiveness of our method, we conducted experiments using two primary datasets: the OLMO2 pretraining corpus for English and the MADLAD 400 dataset for Chinese. We sampled random prefixes from these documents with lengths of up to 1,000 characters for English and 500 characters for Chinese to compute next character distributions using various methods including our Byte sampler. The evaluation metrics included cross-entropy loss and next character prediction accuracy, allowing us to compare the performance of our method against both naive approaches and advanced backtracking methods. We reported average losses and accuracies over 100,000 samples for each language, demonstrating that our method nearly matched the performance of the original token-based model while significantly outperforming naive methods. Additionally, we explored applications such as byte-level ensembles and proxy-tuning, further showcasing the versatility and effectiveness of our approach across different tasks.
What limitations or drawbacks have you identified in your proposed method, and how do these constraints affect its applicability in real-world scenarios?
The proposed method, while addressing the prompt boundary problem, PBP effectively, has some limitations that affect its real-world applicability. One significant constraint is the computational overhead associated with generating text 1 byte at a time, which is inherently slower than token-level sampling, as noted in Section 6. This slower performance can hinder the efficiency of applications requiring rapid text generation. Additionally, while the method allows for the unification of vocabularies across different models, it may still introduce biases in the sampling distribution when combining predictions from models with mismatched tokenizers, as discussed in Section 8. Furthermore, the complexity of maintaining the valid covering tree can lead to challenges in scaling the method for larger models or more extensive datasets. These factors collectively limit the method's practicality in high-demand environments where speed and accuracy are critical.